6.3 is exponential functions. We're going to learn about evaluating exponential functions, how to figure out what the value is going to be when you put a value in. We're going to talk about the graph of exponential functions. I don't like putting a lot of time into the graph just because graphing stuff, I mean, we've learned how to graph any function kind of at this point of deciding what values you need to put in for x and determine the y. But we're going to talk about the basic shape and some of the properties. And we'll even go into some of the shifts that can happen for the graph, how does it move up and down, left and right, stuff like that. We're going to talk about the number e, which is Euler's number. So we're going to talk about that. And then we're going to learn how to solve exponential equations, those are really neat just because when you first see one like it, it's like, how the heck do I do this? But it's really not that bad once we get going. So the first thing that I want to do is I want to review the laws of exponents. We talked about these all the way back in the R sections, probably the first couple of weeks of class. But I like to review them now since it's been so long. And so we got these variables S, T, A, and B. They're all real numbers, but we do have the extra rule that B and A are both greater than 0. We just don't want them to be 0. We don't want them to be negative. If you have A raised to the S times A raised to the T, what do you do with those exponents? Anybody know? It's on there. You're going to add them together. So if you have A raised to the S times A raised to the T, you're going to have A raised to the S plus T. Just like if you had x squared times x to the third. What do you do when you multiply those together? You add that up to be x to the fifth. Same concept. Next one is, let's go this way. If you have A raised to the S and then that's raised to the T, you're going to multiply those exponents together. So you're going to have A raised to the S times T. And so a good example of that is you have x to the third, that's raised to the fifth, that's going to equal x to the 3 times 5, be x raised to the 15. All right. Distributing an exponent, that's one that always gets people. If you have A times B and S raised to S, you can distribute that exponent. Same thing for division. If you have A over B raised to the third power, you can make that A to the third over B to the third. It works for division, it works for multiplication. It does not work for addition or subtraction. You have x minus 2 squared, that does not equal x squared minus 2 squared. Hopefully you know what it does equal. It's what x squared minus 4x plus 4. If you use FOIL to expand it out, which is not the same as this. So it doesn't work for subtraction. It doesn't work for addition. For those, you would need to use FOIL, or however else, there we go. You would expand that polynomial raised to that power. But if it's division or multiplication, it can distribute. Any questions on that? Next one's pretty simple. If you have 1 raised to any power, it's just going to be 1. I don't care how large that power is. This is going to be 1 times 1 times 1 times 1 times 1 times 1 times 1. As many times as I want to do that, it's still going to be 1. Not much to it. This one I think we talked about earlier in the semester. You have A raised to the negative S. So A raised to a negative exponent. That's the same thing as 1 over A to the S, which is the same thing as 1 over A, the whole fraction, raised to the S. Remember that you reciprocate it, you bring it to the other side of the division. Any questions on that? Because we're definitely going to be using that one. So if you have 3 raised to the negative x, how else can we write that?
1 over 3.
Correct. write it 1 over 3 to the x, or we could write it as 1 over 3 and the whole thing raised to x. Okay. Because if we apply that x to the 1, that's still going to be 1. Doesn't matter what x. We're definitely going to be using that. Any questions on that? And the last one. Okay, there we go. If you have a base raised to 0, it's always going to equal 1. Okay. And people always ask me, like, well, how is that? Well, remember that if we have a raised to the s divided by a raised to the t, what does that equal? Anybody remember? It's kind of like the first one we did, but instead of multiplication, it's division. So instead of adding them, we're just subtracting. So it's going to be a to the s minus t, right? And so what if I did a to the third over a to the third? Well, first off, we know it's the same thing over itself, right? So if we did that division, we would get 1. But if we did like this, it's going to be a to the 0. And so we know that's 1. So there's a quick little, I don't want to say proof, but just kind of an example of why that is, in case you're ever curious about it. That's one of those ones that always, that and what's the other one? 0 factorial. That's the only one that gets people. But we don't talk about that in this class. Any questions on any of those? And one of the other things I want to talk about is a little bit of difference with the negatives. So -3 squared is not the same thing as -3 squared. Okay. On the left-hand side there, what you're doing is you're squaring the 3 and then applying a negative. So this is -9. On the right-hand side, you're taking -3 and squaring that -3. And so that's going to be -3 times -3, which is going to be positive. Okay. So be careful of that. If there's no parentheses, assume the negative is outside of the exponent. And when you write stuff, you should write it that way too, just to get any type of ambiguity out of question. Any questions on that? All right. If you do have questions, make sure to let me know. Stop me, whatever. All right. Now we stick with blue. So let's talk about the graph of exponential functions. So the graphs of exponential functions fit into 2 categories, and we're going to talk about both those categories. They look similar. It's just one's doing one thing, one's doing the other thing. But some of the properties of them kind of, I don't know, they're in common, but there's a little difference between them. So let's talk about the form of it. An exponential function is a function of the form f of x is equal to c times a to the x. Now you can have, you can have a plus something on there as well. That's totally fine. But the basic form is c times a to the x. And we're going to talk about what happens if you have a plus b or a minus b. I think they use d. I know what they do, but plus d and minus d. Now there are some limitations to this. We want a to be a positive number. So a is not going to be 0. Because 0 raised to any power is 0 times 0 times 0 is just be 0. And we also don't want it to be negative. Anybody can think why we don't want it to be negative? Well, if the x was negative, right? What if the a was negative? But you're right, if the x was negative, you could have fraction. Anybody know? Well, what if it was? What if my a was? Let's keep doing -3. That's on my mind. Then, so we'd have f of x is equal to -3 raised to x, right? when x is 1, y is going to be what? Well, let's not start with 1. Let's start with 0, actually. Sorry. What is it going to be then? It's going to be 1, remember? Because it's okay. So it's going to be a 1. And then if x was 1, what is y going to be? You had that one already. What was it? 9. It's going to be -3, right? Oh, yeah. It's fine. Now, what if it's 2? 9. That's going to be +9. What if it's 3? 18. What negative? Negative, close. What's 3 times 9? 27. And what if it was 4? Yeah. What if it's raised to the 4th power? What's that going to be? 3 times 3 times, well, -3 times -3 times -3 times -3. 81, right? I mean, 9 times 9 is going to be 81. But what's the problem that's happening there? You see a problem? It's negative and positive. Yeah, so we're oscillating between negative, well, positive, negative, whoa, positive, right? So that's why we don't want that negative base, because it's going to oscillate between this value, this value. Oh, it's going to be closer at first. This value, this value, this value, this value, this value. It's going to keep doing that. And how can we make a function like that? That's kind of just chaos. And so that's why we have that limitation of that a value needs to be greater than 0. It needs to be a positive real number. So it's not negative, not 0. Okay. Any questions on that? And one thing I forgot to say, and I keep wanting to say it, but I realize I haven't introduced you up here. What do y'all think we call that a in an exponential function? Anybody know? A is what I like to call the base. Okay? It's that base number, wow, it's that base number raised to a power. So we're going to call that the base. And I'm going to continue using the term base when we talk about exponential functions and what we talk about in 6.4. So that's why I like to get that out of the way. So that way you know what I'm talking about. Oh, they say it right here. Look at that. The base A. So let's continue on. The next thing is we don't want A to be equal to 1, because that would be a very boring function. It would just be 1 all the way across. So we don't want that to be the case. We don't want C to equal 0, because then the whole thing would just be 0 all the time. So those are the limitations we have. The domain, what do y'all think the domain is of that? Without even looking. It's negative infinity, positive infinity. I can raise it to whatever power I want, right? There's no restrictions on that. I can raise it to a negative value. I can raise it to a positive value. I can raise it to the 0 power. That's totally fine. We know how to do all that. The base A is what we call the growth factor. Depending on how large A is or how small A is, that's going to tell us how fast is it going to grow. Okay? So that's why it can't be negative. It's another reason why it can't be negative. So if you look at different functions, and let's not look at them right now, but if you have a larger base, it's going to grow faster, right? Because if your base is like 2, and 2 is going to start out at 2 to the 0, which is 1, then 2 to the 1, which is 2, then it's going to go to 4, it's going to go to 8, it's going to go to 16, 32. So that's not growing too fast. But look at what we did with the 3. If we looked at positive 3, it would be 1, 3, 9, 27, 81, and then what is it after that? I don't remember. What's 3 raised to the 5th? 243. And so it grows really fast. If we did a base of, let's say, 10, you'd have 1, 10, 100, 1,000, 10,000, 100,000, million. So that's growing super fast. Okay. So that A is going to tell us how fast is it going to grow. Because, oh, I'm erasing stuff. Because f of 0 is going to be C times A raised to the 0, which A raised to the 0 is going to be what? 1 all the time. So f of 0 is always going to be C. Whatever that coefficient on the front is, we call C the initial value. It's the value we're going to start at. Now there are values on the negative side. But the reason that we call this the initial value is that exponential functions are used a lot in modeling things. And when you model stuff, usually you don't start at like a negative time, right? You start at time 0. And so your initial value is what C is. Any questions on that? So we talked about growth factor. We talked about all that. What are exponential functions used for? A ton of stuff. Exponential functions, probably the one you've heard a lot about was when the virus first started. It had exponential growth. Like everybody was worried about it being exponential growth, and it did for a little while, but then it kind of leveled off. You have population. Population growth is usually exponential growth unless it's limited by something else. What's the other things? That's more. Yeah, I guess we can use that. But another thing is sometimes it's not growing. Sometimes it's decreasing, and we'll talk about that as well. Those are going to have exponential. Anybody knows what it's called? Exponential. Instead of exponential growth, there's exponential. Everybody know? It's decay. So like something's decaying, like you know, and that's used for body temperature to figure out how long someone's been dead for. Cooling things in a refrigerator, even is it C14 carbon dating? That's exponential decay, and radioactive decay. Any type of radioactive decay is going to be exponential decay. So this stuff has a ton of real-world uses, and that's really what we cover, especially in the sciences, which all should be either science or business majors. Any questions on that? That's kind of why I like this stuff. I love modeling. That's like, all right. So, what are we doing here? So here we're assuming that we have the functions where C is equal to 5 and A is equal to 2. So it's going to be this function right here. Give me a pen. There we go. F of x is equal to 5 times 2 raised to x. And so if we look at the data for that one, when x is 0, y is going to be 5. That's going to be our initial value. That's the value we start at when x is 0. If x is 1, we have 2 raised to the 1, which is 2, times 5, which is going to be 10. When x is 2, the y value is going to be 20. When x is 3, the y value is going to be 40. And when x is 4, the y value is going to be 80. So you can see how that's grown, right? It starts at 5, grows to 10, grows to 20, grows to 40, grows to 80. And it's a large increase. It's growing exponentially. Okay. Any questions on that? What if we wanted to see the other side of it? What's going to be y when x is negative 1? Yeah, let's work it out. It's going to be 5 times 2 raised to negative 1. What's 2 raised to negative 1? So what happens when you have something raised to a negative exponent? You're going to flip it, right? You're going to reciprocate that. And so this is the same thing as 5 times 1 over 2, which is just going to be 5 halves, which is, what, is that 2.5? Yeah. So notice it is less than our initial value, right? Which makes sense because it should be growing as it progresses. What about negative 2? That's going to be 5. We'll come over here a little bit. 5 times 2 raised to the negative 2. It's going to be 5 times 1 over 4. Oh, sorry, I wrote a 2 instead of a 5. Which is going to be 5 over 4, which is 1 point something, huh? What was it? 1.25. 1.25. Oh, yeah, that makes sense. 1.25. It'd be 1 and 1/4. 1.25. And we can keep going. But you can see how, as you go to the left, it's decreasing, right? So that's why it's exponential growth. It's going to start, and then it's going to boom up. That's basically what it looks like. We're going to look at some graphs in a bit. Any questions on that? Man, these Monday, Wednesday, Friday goes by so fast. All right, let me zoom out a little bit. Okay, so we're going to start with a pretty basic one than what we were just looking at. We're just going to look at 2 raised to the x. So let's talk about what each part is. The exponent is just x in this case, right? It could be x plus 1, it could be 2x, it could be some function of x, but in this case it's just x. And that's what makes it an exponential function, is that the variable is in the exponent. It makes sense, right? Variable is in the exponent, it's an exponential function. Boom. What is the base here? 2, right? 2 raised. We don't have an initial value. We'll talk about that in a bit. But the base is 2, so that means that my growth factor is going to be 2. What is the initial value? Nope.
Nothing.
Is what?
Nothing.
I mean, there's nothing written there, but what would you?
Oh, you assume 1?
It would assume 1. So we have an initial value of 1. So that means f of 0 should be 1 in this case, right? Which makes sense because 2 raised to the 0 power is going to be 1. So that's some of the stuff that you have to look for to get a feel for it. And if we look at these, we could get some values. I already have the values here, but you can do it in your calculator. 2 raised to the negative 10, that's going to give you 0.00098. Is a very small decimal. To the negative 3 is going to be 1 over 8, which I don't know. What is 1 over 8? 0.125. Just write that out. 1 over 4, which is going to be 0.25. 1/2, which is 0.5. And then notice that once the x values are no longer negative, now we don't have any more decimals, we don't have any more fractions. We're going to have 2 raised to the 0, that's 1, that's our initial value. Let's write IV here, initial value. Then we're going to have 2 to the 1, which is 2, 2 squared, which is 4, 2 to the 3rd, which is 8. And then we're going to skip a few. 2 to the 10th is 1024. And so this is what a graph looks like. And this is what we call exponential growth. Let me try to write it because I misspelled growth somehow. So that's exponential growth. You can see how it's just booming, right? It just takes off. Like a ramp. Any questions on that? If anybody does any type of computer science stuff, 2 to the power is a big thing. You may recognize the 1024. That's how many, what, bytes are in a gig? 1024, is that right? That'd be a megabyte, yeah. It's 1024 megabytes is in a gig. They say 1,000 to make it easier to say 1024. Oh, here we go. This function has what we call exponential growth. Any questions on that? So if you know what the basic shape of it is, if it's exponential growth, it's going to have this basic shape. It may be shifted, which we'll talk about later, up or down, but you know you'll have that initial value happening at one point, and then it's going to grow as you go to the right. All right. So let's talk about some properties of that. Can't really put them all both on the screen, can I? No, that's all one thing. We'll go back and forth. So these are some properties of that. The properties of the exponential function, we're going to break it up into 2 things. The first one is when a is greater than 1. Now remember, we said already that a had to be greater than 0, but we're breaking it up further. We're saying these are the properties that apply when a is greater than 1. So when your base is greater than 1, we don't want it to equal 1, and we want it to be greater than 0 already. But this is where we're just looking where it's greater than 1. So the first thing I want to say is that it's exponential growth. So when you have f of x equal to a times x, a raised to the x, it's going to be exponential growth when a is greater than 1. And then we have some basic properties from there. Some of these may change if it shifts, but they'll give you a good starting point. First one is the domain. The domain is the set of all real numbers. We talked about that before. That's not going to change. It's going to be negative infinity to positive infinity. The range is going to be from what? Anybody know? It's going to be from 0 to positive infinity, but it won't include 0. I can't raise a number to a power and get 0. So it's going to be 0 with a parenthesis all the way to positive infinity. Now, if the graph was shifted down 1 unit, then it would be from -1 to infinity. If the graph was shifted up 3 units, it would be from 3 to infinity. Okay? So if that shift happens, it can change that up. It won't change the domain, though. It'll just change the range. All right, for the basic one, there are no x-intercepts because it gets close to 0, but it never actually hits it. The y-intercept is going to be 1. The y-intercept is going to be your initial value, which in this case is 1. But if your initial value was 3, the y-intercept is going to be 3. Kind of like the one we saw earlier where the initial value was 5. Remember we had the point 0, 5. The y-intercept would be 5. Three, the x-axis, y equals 0, is the horizontal asymptote. Okay, y'all don't know anything about limits yet, so disregard that. But that's going to be the horizontal asymptote. Which if we look here, what that means is that it's going to get closer and closer to that line, but never actually intersect it. It's never going to actually touch it. It's going to get closer and closer and closer and closer as we go along, but never actually touch it. Now that may shift, like I said, if the graph shifts up or down, it may shift as well. This is important. F of x is equal to a to the x when a is greater than 1 is an increasing function, exponential growth, it's increasing, and is 1 to 1. That's going to be important when we get to 6.4. It's a 1 to 1 function. Remember, if a function is always increasing, it's going to be 1 to 1. If it's always decreasing, it's also 1 to 1. The graph contains these specific points. Now, that's if your initial value is 1 and some other stuff's not happening. But if it's a basic f of x is equal to a to the x form function, you have -1, 1 over a. You have 0, 1, and 1, a. That's some points on your graph. And the last one, f is a smooth and continuous. There's no corners or gaps. There's no splits or jumps or anything like that. It just goes whoop, whoop, and continues going. The only time we talked about continuity, did we talk about continuity in here? Not so much, no. Any questions on that? So that's some stuff that you can use to graph it or determine what function the graph is from. That will help you out. So if we want to graph one, and this time, the last time we looked at, it was a base of 2, right? This time we're going to look where the base is 1/2. Now remember, that's the same thing as having it as 2 raised to the -x, right? So if you do have one with a negative exponent, I would say convert it so you have a positive exponent. Because if we look at these values, when we raise it to a -10, we're going to have 10/24. -3, we're going to have 8. -2, we're gonna have 4, -1, we're gonna have 2. And then notice when we get to 0, we still have that 1. We still have that initial value. Boom. But what's interesting, remember that, is when we go to 1, now it's gonna be 1/2, 2, 1/4, 3, 1/8, 10, we have that 0.00098. Whenever your base is less than 1, it also still has to be greater than 0, it can't equal 1, but when it's less than 1, when it's a fraction or a decimal that's less than 1, your graph is going to look like this, and we're going to call that exponential decay. There's 2 types of graphs you can see: exponential growth, exponential decay. It's all based on what the base is. That's kind of that way. It's all about what the base is. The base is greater than 1, exponential growth. If the base is less than 1, exponential decay. Questions on that? You can see that it's almost like that graph, exponential growth, flipped around, right? So you take it and you just go flip it around. Because exponential growth will go like that, but it's exponentially decaying. That's the one we use for like body temperature. How long will it take for things to cool? I think I use that one. I don't remember. It's been a while since we've done a problem like that. And radioactive decay, carbon dating. It's all about how many years does it take to go from 1/2 to 1/4, and then we figure out if it's gone there. Any questions on that? All right, let's look at the properties of those. Probably won't even get to that. Let's go over these properties and call it, I guess. So, if you have one of the form, there we go. F of x is equal to a to the x, but a is between 0 and 1. So a is some fraction, decimal, less than 1. Okay, I keep saying less than 1 as well because you could have a fraction that's greater than 1. 5/4 is greater than 1. And that would be exponential growth. So it needs to be less than 1. The domain, still going to be all reals. X to be whatever it wants. The range, still from 0 to positive infinity. It starts at positive infinity and then it gets closer to 0. Rather than the other one started at 0 and went to positive infinity. There are no x-intercepts once again. That may change if it's shifted down. The y-intercept is still 1. The y-intercept is still going to be that initial value. Whatever the initial value. Unless it moves up or down, or the initial value is not 1. If the initial value was 5, then my y-intercept is 5. And if it was 5 and then shifted up 1, what do you think the initial value would be? 6, yeah. Perfect. The x-axis, that's still going to be a horizontal asymptote, unless it's shifted up or down, but you can see here, it's going to decay and get closer and closer and closer and closer. It's never going to actually intersect that line. It's a decreasing function, and it's 1-to-1. It's exponential decay. It's decaying. It's decreasing. And if you have a function that's constantly decreasing, or it's always decreasing, that's a better way of saying it, it is going to be 1-to-1. Notice that the points are the same. We have -1, 1/8. 0 on 1, and 1 comma a. Those are your basic points. But like I said before, those could shift depending on your function. They're just a good set of points to look at. Is to look at when x is -1, x is 0, and x is 1. Those are usually pretty good to look at. And then once again, it's smooth and continuous. There's no gaps, no jumps or anything. I always think about it as like the exponential growth. It's like you're on a roller coaster and you're just shooting up. And then the exponential decay is like you're coming back down. So it's like one ramps you up and the other one brings you back down.